Hello Year 10. Today's lesson is about elastic potential energy, which is the energy in stretched objects. And you can see this gentleman on a bungee. Brilliant picture, launched off over the sea, hands outstretched and plummeting towards the surface of the water. Let's move on. So, what is elastic potential energy? All objects that are elastic and have been stretched or compressed store elastic potential energy. What is an elastic object or an elastic material? These are materials that if they're stretched or they're compressed, they will try and return to their original shape and size. So an elastic band, for example, if you stretch an elastic band and let go, it tries to return back to its original shape and size. If you squash a rubber ball, it will try and return back to its original shape and size if you let it go again. The more that you stretch or compress elastic materials, the more elastic energy they store. There is an equation for elastic energy which is being highlighted. E equals 1/2 times K times E squared. In AQA, we use this notation of E subscript E for elastic energy. You might see in books though, elastic potential energy, which is EPE. K is something called the spring constant, which represents how stiff the spring is. The stiffer the spring, the bigger the value of K. And we use the letter E to represent the extension, and that must be in meters. Now this equation looks very much like the equation for kinetic energy, and it's quite easy to get them mixed up unless you learn your equations. Okay, otherwise you're going to get this easily confused with EK equals 1/2 mv squared. Okay, so please don't make that mistake. So how do we calculate the extension? Extension is represented by E, okay, and it's E squared at the end. The first thing to say is that the extension must be converted to meters. The extension is how much a spring stretches. So it's not the whole length of the spring. And I've got an example at the bottom here to explain what I mean. We've got a spring which is 2 centimeters long. It's stretched so that it is now 3 centimeters long. The extension is 1 centimeter, 3 centimeters minus 2, which equals 1. And that has to be converted to meters. So in fact, the extension is 0.01 meters. There is a very simple formula for this. The extension equals the new length minus the original length. If you compress the spring, the extension will be negative, but that won't affect the energy because if you put a negative number into E squared, it becomes positive again. Okay? So which of these has the most EPE or EE if we're using AQA? Well, look at the monster truck there. We've got the compression, so let's quickly show you how you would work that out. Okay, so EE equals 1/2 times K, which is 5,000 times 0.1 squared. Okay, and that's equal to 25 joules. If we did the same thing for the elephant on a pogo stick, which I know is a very silly example, we've got 1/2 times 200 times 0.2 squared, and that equals 4 joules. So the monster truck has got much more elastic energy stored in the springs. All of these objects have elastic energy stored in them. I think we may have used the poppers in lesson. I think we've maybe used those in the classroom. Catapults, rubber balls, suspension springs for cars, exercise machines, clockwork, and this is Oscar Pistorius, the infamous Blade Runner, and the elastic energy stored in the blades. Okay, let's consider the energy changes in a bungee jump. So there are 4 different situations here, and which diagram has got the most gravitational potential? Well, that must be A, because they're the highest. Okay, biggest height, therefore the biggest gravitational potential. They're not moving, so no KE. The bungee's not stretched, so no EPE. Which diagram has got the most EPE? Well, C does, because the bungee rope is fully stretched. They're at the bottom, they're not moving, so no KE, and they're at the bottom, so there's no GPE. So all the energy has been converted to elastic potential energy. Finally, which diagram has the most KE? B does, because this is the bungee rope is not stretched yet. They're falling with maximum velocity, so they have the biggest KE. If we were in class, I would get you to do a practical activity where we load up a spring and we measure the original length and the new length. We calculate the extension in centimeters first, then in meters, and then we calculate the EPE. Okay, we use the same spring all the time, which has a spring constant K of 25 newtons per meter. Okay, that's what we would do if we were in the lab. Right, let's see if we can put the missing words in. This is very straightforward. Elastic potential energy is the energy stored in anything that is stretched or squashed. Better to use compressed. The amount of energy depends on how much the thing is stretched or squashed by. We call this the extension. To work out the extension, you do extension equals new length minus original length. I'm just going to highlight that because that is a formula. The extension is measured in meters. The elastic potential also depends on spring constant, which tells us how difficult it is to stretch the thing. Okay, this is some work, which those are the answers that you might need for it. I'm going to put some practice calculations onto its learning. I'm going to put some past paper questions on there as well. So please do practice using this formula, and I wish you all the best and thank you for listening.